Welcome to this video. We will talk about template classes in this video. Let's start with a recap of what we did last time. So we were talking about template functions and we said that template functions are a form of compile time polymorphism in C++, and they allow code reuse in the sense that you write one piece of code and you can run it on multiple different data types. And the template functions can have parameters, which could be type parameters or placeholders for different data types, or they could be non-type parameters as well, for example, constants. And we also saw that you can have specialized versions of the template functions in the sense that one particular implementation will be called in certain specific cases, for example, specific types of data, whereas the other more general implementation of the template function would be used in other cases. And the thing is that the template syntax can also be applied to classes or the code that defines classes as well. And what this would enable us to do is that member variables could be defined to be of type that is a template parameter. And member functions could be defined such that the arguments, some of the arguments are of template types, or their return values could be of different data types. And this is especially useful for something known as container classes. And these are classes that can contain instances of other classes like arrays or linked lists hold instances of other types of data. So let's see an example of creating a template class. So here's our sample program. It is a class named vector, and it is going to hold a dynamic array for integers. So here we have a pointer of type int, so that is going to hold the address of the dynamically allocated array that stores those integers. This here is a variable that will store the number of integers actually stored in that array, and this here is the capacity. So in the constructor, what we're doing is accepting a parameter and setting a default value for it. So if you don't pass a parameter to the constructor, then default size of 10 will be used for the array. Otherwise, you can pass a parameter for the capacity of the array. We actually create the array over here in the member initializer list. We're setting the value of the variable named ARR to the address of a newly allocated dynamic array of integers of size 10. We're setting the value of the variable capacity equal to the value of the parameter n. And since nothing is stored in this array at this point, we're setting the size member variable to 0. In the destructor, we are delocating this array. um, and I should have an if statement around this delete or before this delete, but for simplicity, I've kept it omitted that one. We have a member named at, which is used to read the array. You pass the index that you want to read from the dynamically allocated array. And this function returns a pointer to the integer stored at that index. I'm defining it as const because we're not going to modify any of the class member variables. If the value of the index that you're passing happens to be above the actual number of elements stored in the array, then we just return a null pointer. Otherwise, we return the address of the value stored at the index n. We have a method to add the values to this dynamically allocated array. You pass in the value that you want to store, and this function will store it to the end of the dynamically allocated array after all the existing values. First of all, what we check is if the array is already full. If that is the case, we double its capacity. We allocate a new array of twice the size as the old one. And then we call a standard C++ library function named copy. And what does that does is it copies data to this pointer passed as the last parameter, which is the newly allocated array. And the data to be copied from is specified in the first two parameters. So the first parameter mentions where you start from, where you start copying from, the source, which is the beginning of the old array, and the ending point, the where you stop copying, uh, and that is being used or specified as ARR plus size, which is the address of the last element in the previous array. Once the copying has been done, we deallocate the old array and we update the value of the member variable ARR to be equal to the address of the newly allocated array. Once all of that is done, what we do is we store the value passed by the user into the array at the last index, which is specified by size. And since we now have one more element in the array, we include size. We also have a method named getSize, which is a getter for the size attribute. Let's see how do we use this class in our program. We include the vec.h file, and inside our main function, I create an object of type vector. And over here, we have a for loop that runs from 0 to 24, and it adds an integer to the vector v using the pushback function. So the values from 1 to 25 will be added to this dynamically allocated array. And then we have a loop that displays all those values to the screen using cout. And this also runs from 0 to 24. And we're calling the add function that we defined in our class, which returns a pointer to an integer. So to get to the actual integer value, we are performing the indirection using the star operator. And then the main function ends with return 0. So let's see how we can run and compile and run this program. I compile it using g++ main.cpp. I am in the correct directory. I run it using /a.out. And what we see on the screen are numbers from 1 all the way to 25, just as expected. Right, so no surprises there. That's something that we've been doing all along, right? But that has nothing to do with template classes. So that was just our starting point. We have a class that manages a dynamically allocated array of type int. Now we want to generalize it so that it's a dynamically allocated array of any particular type. So let's see how we can do that. We use the template syntax before the definition of the class. I say template type name t, and then, since this is the type of the dynamically allocated array, I'm going to change it from int to the template parameter t. So that this will be an array of any type that you specialize or instantiate the template class with. I don't have to change the size or the capacity because these are just unsigned integers, and that's true for any kind of array. Here's where the constructor is. The constructor parameter is the size of the array. The size is size underscore t, no matter what type of array you are allocating. However, over here you are allocating the specific array of type int. That is not general. So we're going to change the int with a t. So now you are allocating a dynamic array of any particular type. All the other parameters don't need to change. The destructor, you don't need to change anything there because the data type is not mentioned anywhere at all. In the add function, the argument is an index, which is type size underscore t. No need to change that. However, you were previously returning a pointer to an int. Now you'll return a pointer to the type t. Other than that, there is no mention of the particular data type inside this function's definition, so no changes there. The pushback function adds a new value to the array. So this particular argument, which is of type int, needs to change to t so that it is general, can be any different, any data type at all. And over here, we are allocating a new array of that type. So the int needs to be replaced with t here as well. And the int pointer needs to be changed to t pointer. Other than that, these functions work just as fine. And finally, the get size is a getter for the size attribute, and that is still size type of type size underscore t. So there's no change needed at this point. Let's go ahead and save this file and see how we can use it in the main function. First of all, let's see if we don't make any changes to the main function over here, do we get any errors or not? Switching over to our terminal. Let's see what happens if I compile the program. Now I'm getting a bunch of complaints from the compiler. It is saying class template argument deduction failed on line number 4 for vector v. So let's switch back to VS Code and see what this is referring to. It's referring to this line, and on this line we are creating an instance of this class vector, but the underlying type of data to be used for the array is not clear from this variable definition or object definition. So what we need to do is to specify that template parameter. And in this case, I'm using int because that's what I am passing. That's the type of data I'm passing to the pushback function. So over here, what we're doing is we're matching the definition of the class vector. It accepts one template parameter. That is exactly what we're passing inside these angle brackets. We are declaring a vector of type int. So let's see what happens if we compile this program again. I clear the window and then compile it. Now the program compiles fine, and now I can run it and it runs just as well as it did before. That's great. We can create a dynamically allocated array of integers, but that's nothing new. We've been doing that for a long time. Let's see if we can use this dynamically allocated array, this class that manages one, to create an array of custom data types like our own class. So for example, we have this person class, which has an attribute for the name of the person. It has a set name function that sets the name and a get name function that returns the name, right? And we overload the stream insertion operator less than to be able to display an object of type person. So we take the output stream, use the less than operator on it, and call the p.getName function, which returns the name of the person object, and then we return the output stream object from this function. So inside main, now we can include this header file person.h, and we can leave this handling of integers as it is, and we can create a few objects of type person. I create an object p1, I set its name to John. I create another object p2 and set its name to Jane. And then I create a vector object v2 with the template parameter set to person class. And then I call the v2.pushback method twice. Once I include p1 and then I include p2 or add p2 to that dynamically allocated array managed by the vector class. And then I run a loop twice and calling the add function just like I did for the integers to display the person objects on the screen. So let's see if this program compiles and runs. So let's switch over to the terminal, and over here we compile the program, compiles just fine, and we run it. And now we not only get the 25 numbers on the screen, we also get the person objects displayed on the screen. So that's fantastic. Now we have a template class which manages a container of many different data types, and we can use it in our program to store any kind of objects that we desire.